Hello, everyone. Welcome to the next part of our Trustworthy Machine Learning with Imperfect Data tutorial. Okay, in my part, I will talk about the Trustworthy Machine Learning on adversary data, and I'm Feng from University of Melbourne. So first of all, I will introduce myself a little bit more. My name is Feng. I'm currently assistant professor in machine learning, and some of my major achievements, including the NeurIPS outstanding paper in 2022, and I also obtained the ARC Early Career Researcher Award. And my research interests mainly contain two parts. One is statistical machine learning, one is statistical hypothesis testing. Another is distribution shift related topics. So for the distribution shift topics, I mainly focus on three kinds of shift. The first one is adversary shift. Second one is out of distribution shift. The last one is nature shift. Okay, now let's look at our main topic here today. It's about trustworthy machine learning with adversary data. So first of all, what is adversary data? Okay, we can look at this image. In this image, there's three images here. The left one is a panda image, and the right one is a panda image with some noise. And noise is here, okay? It's noise image plus very small coefficient, so we got a new image. In adversary attack, attackers will learn this kind of noise and add this noise to this panda image. I get a new panda image. However, the previously pre-trained classifier will recognize the left one as panda with a 15.7.7 confidence, okay? But after the adversary attack, we will get this one. It's also panda image from our human eyes, but the previous classifier, will predict this panda as gibbon with very high confidence. That's the adversary attack. It will attack the original images such that the original classifier cannot work well. Okay. Okay, so now let's go back to say what is adversary data? Okay. And in the previous conventional machine learning pipeline, we will have training data with labels. We will train model. This might be neural network or transformer. And in the test phase, we will just input our test data to the well-trained network, right? For example, neural network or transformer, and we got predict labels. Okay, that's a conventional machine learning pipeline. And in adversary attack, we will add some adversary perturbations to the test data and input this image or text with the adversary perturbations to the well-trained model. And we got predict labels. But here, the label is untrusted. Normally, adversary attack can make the prediction accuracy or classification accuracy to achieve 0% accuracy. Yeah, 0% accuracy. It means that it really works. Otherwise, it's might not real 0%, right? It's random guess. Yeah, but it's worse than random guess after the adversary attack. Yeah. Okay. Now we want to think about why it can be successful. We add this small perturbation, right, to the panda image, and still panda image to human eyes. Why it can be successful to the model we trained on the previous images, right? The reason is that adversary data and the nature data have different distributions, okay? And it will cause significant error, okay? Why different distributions will cause significant error? Yeah, we can go back to basic assumption in machine learning. So it's in machine learning, we always have the training set and we'll train a model, okay? And we got and then we just apply the model. Here is a decision line to the right part to help us classify points in test set. Okay. You can say it's very close to the test set ground truth decision boundary. However, this success is based on the basic assumption in machine learning. Training and test have to be same distribution, okay? But in real world, if we look at CFA 10, CFA 10.1 here, it's actually not easy to tell if they are from same distribution. So we may have a question, are they from same distribution? If not, can we use a model trained with CIFAR 10 to help us classify images in CIFAR 10.1? Okay. And if there is indeed distribution or discrepancy, so what we will meet? We can look at this example again. Okay, the left one is our training set, and we train the model. Okay, we train a model. Its model here is just the distance boundary. Yeah, and the right one is a new test set with this as its ground truth decision boundary. Okay, if we directly apply the left one to right one, you can say what will happen. We'll make wrong prediction in this area. Okay, so it will cause significant error here. And that's why adverse attack can be successful. And we also justify this in our previous paper. Okay, like they actually have different distributions. That's why it will cause significant error. Okay, now we know what the adverse attacks are. The next step is how to prevent from adverse attacks. In the literature, we normally have three directions, and they can be grouped by two major directions. Okay, the first one is actively handle adverse data, and one is data perspective. It's called adverse purification. In purification, we want to purify upcoming data such that even for adversary data, it will be purified back to normal data. Okay, adversary noise will be removed. It's called purification. Second way to actively handle adverse data is called model perspective. It's an adverse training. We want to train a model robust to adversary data. Okay. The last one is we want to passively handle adverse data. It's adversary detection. In this scenario, we will detect if the data is adversarial. If it is from attackers, we will just throw it away. We will not make any prediction of that. Okay. So for the for the purification, it happens in the input process. Okay, so we will purify any data such that the adversary noise, the possible adversary noise, will be removed. And for the model perspective, it's we will train a robust model. Okay, it's actually happens here in this pipeline. And for adversary detection, it happens before any training and inference. We will just work on the adversary data itself and to decide which data is adversary and it's not. Okay, for adversary data, we just throw it away.